So in this new video, we're going to look at something called error. Sorry about that, error propagation. So we are seeing two terms here, error propagation. We already saw what an error is. But what is propagation? From our biology, we know that propagation is where you have to, let's say it's beans, you get beans, you plant. How are they propagated? By planting seeds. So that means if you have one seed, that seed is going to grow and bear the fruit, that bean fruit. And inside that fruit, there are more seeds. So it is increasing the seeds. That's propagation. Yeah, now that's propagation in biology. Then propagation also could be looked at like something, or let's say a rumor. If it propagated, then it's the explosion of the rumor being known by many people. Yeah, that means the rumor has propagated. So when we look at error propagation, what we are going to see here is how an error made in obtaining a certain value affects another value. How does it make it the error in the other value grow? Simply, under this section, we are going to look at the effect of making an error on different variables affects the function depending on those variables. For example, given that A is equal to length times width, let's say area, let's say A stands for area, length times width, then making an error in determining the length and the width independently. Let's say you're determining the length and the width, but independently you first measure the length and the width, then you'd multiply the two to get the value of it. There will be an effect on A if the length and the width are not measured accurately. So I go ahead to say that, and the errors delta L and delta W propagate to result in the error delta A. So because the length and the width are not accurate, then therefore the area is also not going to be accurate, but deviating by a certain value from the actual area. So in other words, you will determine the area, let's say of a square field. Yes, of a square field. Let's say this is an instrument that measures the area of a square field. Then you note it down. Then you also measure the length of that okay, it's rectangular because we're looking at length and width. Yeah, let's say it's a rectangular field, sorry. And let's say you obtain the length and the width of that rectangular field. So, and you multiply the length and the width to give you the area. You would realize the values are somehow not the same. They're somehow not the same because you could have made an error in obtaining that length and that width. So that's why you have a deviation from the actual value. And there's no guarantee that if you determine the area using a certain instrument, then that's the actual value. That there's no guarantee as that. But since there even doesn't exist to be an instrument to measure area directly, then you use the parameters. Use the parameters given. Let's say for a cylinder, you measure the radius of the cross section and the length of the cylinder. Then for a rectangular field, you measure the length and width, and then you multiply to get the area, and so on and so forth. But in obtaining those different parameters, you are going to make errors, and those errors are going to mount up to an error in the variable that is depending on those, or on the function that's depending on those variables. In this example I gave, area equals length times width. So area is the function depending on the variables L and W. The moment you make an error in L and W, then you're making an error in the area. So when we say the error has propagated, therefore the error has grown. The error in area has grown because of the error you made in measuring the radius, the length and the width. So under this, we are going to look at another concept. It's called the concept of triangle inequality. Yes, but that is going to be explained within the body of an example. So the example says the area A of a square field, a square field, but we can call it rectangular, is given by A equals to L times W, length times width. with errors delta L and delta W respectively. Show that the maximum possible error in the area is given by. Oh, I did not write that down, but we are going to see eventually what it's given by. So we let the approximate values of the length and width be L and W, capital L and W, because we are going to now derive this from first principles, the basic principles and the basic definitions. So the error delta L will be the approximate value, capital L minus small l. And therefore the approximate value, capital L, is L plus delta L. Same as applied to the width. So if it is the area, what is the error in the area? The error in the area will be the approximated area and the actual area, difference between those two. And when you substitute respectively, you end up with your error in the area as L delta W plus W delta L, and that's our equation 1. And that's our equation 1. I call it equation 1 for a reason we're going to see. So at this point here, you can see that the area made in the, when you are determining the error made in the, when you determine the area of the square field, depends on the error you make when you're determining the width and the error you make as you're determining the length. You can see here, it's in the expression. Yeah, it's in the expression. So the magnitude of the error you make determines also the magnitude. The magnitude of the error you make in determining the length and the width determines the magnitude of the error that is in the area. So now this is where the triangle inequality comes in. And the aim of this triangle inequality, let's look at a triangle. A triangle has three sides, sorry. But then if you add any two sides, then that sum is obviously going to be greater than the value of one side. So let's say I had the triangle ABC. Yeah, if one side is A, another is B, another is C. So if you add A to B, then the magnitude of this sum is definitely going to be greater than the other side, may be greater than or equal to, depending on the construction of the triangle. So it's the same thing as applied to this area. Yeah, the magnitude, okay, we have obtained and seen that the error in the area depends on these two values. But then you should realize the error you make in the area will never be greater than the sum of the errors, independent errors you're going to make in length and width. So for example, as I said, if you had a way of determining this area of this field, then the error you're going to make in determining the area let's say you're using an instrument to determine the area of that field, is a standard instrument, then the error you'll make in determining the area will be different. Yeah, the first case you're going to determine the area using an instrument, and the second case is you're going to determine the length and the width, and then you multiply the two to obtain the area. So, but it is going to be different. The errors are going to be different, and that is what the triangle inequality is. That's how it is introduced, such that the error in the area is always going to be less or equal to the error that you're going to make as if you determine the length and the width independently. So because now the area also depends on the error you make. The error in the area depends on the error you make in the length and in the width. So in the triangle inequality is going to just satisfy that, and it's going to just not prove actually, but it's just used as a notation. It's used as, that's what the statement means. The absolute error in the area is less than or equal to the absolute error in these terms. Yeah, and furthermore, the absolute area is less than or equal to the sum of the absolute values, the independent absolute values of the expression in one. And therefore, so that means the error is either less than the sum of those two, or it's going to be equal to the sum of those two. But now the question has asked for the maximum possible error The maximum possible error, therefore, is we're going to look at these two scenarios and conclude which one is maximum. So the error in the area is going to be maximum when when it is equal to the modulus of L delta W plus the modulus of, no, I repeated, of W delta L, sorry. This, even this, yeah, this is W delta L, same as applied to this, W delta L, and this is also W delta L. Yeah, and therefore our maximum possible error in determining the area is that, yeah, also here it's supposed to be W delta L, W delta L. So yes, that is how we would go about that. So that's the principle of error propagation. How is the area? I mean, how is the error made in a certain variable affecting the function? Yeah, yes, and that's how we would go about that.